Rutherford's gold foil experiment. Yesterday, or the last time when we met, we talked about Dalton's model of the atom, which was a sphere that had a consistent density throughout, and he did not know about any of the positive or negative charges. J.J. Thomson came along and did some more work and found that using the cathode ray tube that there were these electrons. And then he noticed also that there were some positive charges. So Thomson's model of the atom was evolved or changed into what we see now. Everybody good here? Yes. Okay. A lot of chatter here. All right. So looking at the atom, this is Thomson's model of the atom, where we have this, still the sphere, but we have these negatively charged particles and some positive charges involved here. Rutherford said, you know what, Thomson, I really like what you've got here. I'm going to help you out. I'm going to be a good friend, and I'm going to show that your model is correct. So he came up with this gold foil experiment. Find it. And what he did was, he had this piece of gold foil. Okay, they say metal foil in your notes, but it was actually the gold foil experiment. He set up this piece of gold foil and put this photosensitive material around. I don't know why he actually put it all the way around, but he did. I'm glad he did, on accident. And then he had a source that generated alpha particles, and we'll talk about how you can do that in a couple of weeks. You're not going to do it at home, so don't think, oh yeah, I'm going to do this. And based on the model that Thomson had, let's keep this in my hand, based on the model that Thomson had with all these particles scattered throughout the atom, Rutherford said, okay, what's going to happen is I'm going to shoot these alpha particles, which is nothing but a helium atom with no electrons, and as they pass through the gold foil, most of the particles should go straight on through, okay? Because again, we know that atoms are mostly empty space. A few of them will be deflected, because just like if you've ever played pool and you've hit a ball on the side and it kind of ricochets off, that's what should happen with these as well. What he did not expect was that when he shot this alpha particle and it hit one of those particles, whether an electron or a proton, and it shot backward. Here, I'm going to put it in modern terms. The proton or the electron, and again, much different masses, so we'll say an electron, is a smart car, a parked smart car, in the middle of I-465. Okay? About a mile down the road, there's this tractor trailer, 18-wheeler, carrying concrete blocks going about 80 miles an hour, headed right for the smart car. As it gets closer and closer, the driver in the smart car, which is pointed directly in the wrong direction, pointed toward this truck, is confident. It's like, Thomson's got my back. Okay? So as this tractor trailer engages the smart car, it hits and is thrown back. Smart car sits there nice and smug. Is that normal?
No.
No. And that's what Rutherford thought. There is no way that I'm going to shoot an alpha particle that has a mass that's at least 4 times more than any of those particles standing alone inside of the atom and will cause it to deflect backward. So Rutherford said, you know what? I'm not happy with what you're saying here, Thomson. We're friends and all, but I've got to revise your model. And he did something like this. He said, you know what, I like that you got all these positive and negative charges in here, but there's something in the middle. There's something that's more massive that can take that crash of the alpha particle and cause it to deflect backward. And so Rutherford came up with the nucleus for your atom. Here's a neat little animation. I didn't make it, but it's...
What's an alpha particle?
An alpha particle is a helium atom with no electrons. So here's what Thomson's model looked like. Really exciting. The plum pudding pie model. Here's what Rutherford, when he was shooting these alpha particles, oops, let's shut that up. Like the sound effects, that's good. Okay, so most of them, as he expected, the red dots are your alpha particles. Most of them pass straight on through. A couple were deflected off ever so slightly. That's what Rutherford expected. All right. What actually happened So, set up the chamber. Most of them passed straight on through. A couple were deflected, but every once in a while, one would get hit backward. That was huge. The only way that could happen is if you had something massive in the central and it was a direct hit. So Rutherford's model was made up so that we had this central core, and again, this is not to scale, but again, it does a nice job in representing. Come on, start shooting. Maybe it'll start if you do the sound effects, actually. There you go. That. So again, most of them pass straight on through. A direct hit will cause it to deflect backward. A side shot will cause it to move on, just like if you were playing pool. Okay, so that is the only thing that could explain how something so massive could hit a subatomic particle and be able to be deflected backward. If you want to look at that video, it's linked to the calendar. All right, did everybody get the blank so far? Deflecting and deflecting back. Okay.
The room is freezing.
Sorry.
But all the other ones are hot. There's no hot either.
So Rutherford explained, all right, for this to take place, there has to be a core, a centrally located core, something massive. And especially when you look at gold, gold's atomic number is 79, and it has a mass of almost 200. So there's a lot of particles in the middle of that atom. Okay, that would help to support that deflection back. If you think of, and again, there might be another model that you can associate this with. The small dense central core of positive charge had 99.9% of the atom's mass. In other words, an atom is mostly made up of empty space. There's another model that we currently reside within that has a similar setup, where 99% of the mass of this system is located in the sun. Our own solar system, 99% of the mass is in the sun. And then the planets and the other debris make up the rest of it. It's not very much, but the sun has a lot of that. Wow, nice A's. So when we look at the small microscopic scale, I mean really small, so small we can't see it, it has the same model, same arrangement as our solar system. All right, so that's pretty cool. And even if you look at the galaxy, the center of the galaxy is very, very massive, but I don't think it's around 99%. So electrons move around the nucleus like bees around a hive. Rutherford calculated the diameter of a nucleus to be 1/1000th. So I'm talking, this central core is massive. Not huge, it's massive. Now mass deals with weight. If we were to put it into perspective, if this were the nucleus of a hydrogen atom, okay, the nucleus, just in that we have one proton and one neutron. Actually, we don't even have a neutron in there, it's just one proton. There's one electron that's with this hydrogen atom. If we were to scale, where would the first electron be located? About where my head is? About where Stephanie's at? What's really far? To the moon? Wow, that's really far. To who? To Ashley? Well, that's about Stephanie. Actually, everybody know where Central, or I'm sorry, not Central, but I'm drawing a blank. Hickory and Cedar, that's the ones.
Yeah.
Those elementaries. That would be, that radius would be where the electron's at.
What?
That would be the center.
This would be the center, and then where Hickory and Cedar are at, that would be our first electron. Actually, the one electron. So it's really far away.
Okay, so
Go ahead.
we're made up,
Lots of these.
so that means like a bunch of diameters are like overlapping.
Not overlapping. Actually, if you look at these, notice how they don't overlap.
No. Like,
Okay.
Okay, so you've got like a center here,
Mm-hmm.
and like a center here, like over there. So aren't our diameters gonna touch?
This is not the scale. I'm gonna answer your question with another question. That's our center. This is not to scale. So our first electron would be cedar and hickory. The next atom cannot get, the nucleus cannot get in that same circle or that sphere of the atom.
But I thought
they were really small.
They're really small, but I'm putting it to scale so you can see this.
So like.
So if this is the nucleus,
Real life, how far away would it be?
oh, we're talking picometers.
Oh.
Yeah. But to scale, this is the nucleus. The first electron is around cedar or hickory.
okay, so for real, like
For real, it's itty bitty.
there's a bunch of atoms in here,
In you.
in me.
Oh, yeah. Now, here's a nice thought. You're going to really like this. But you are mostly made up of what?
Water.
Empty space.
In our bodies.
Everything. Yep. Everything that we deal with is made up of mostly empty space. Think about this. Okay, this remote that I'm holding might weigh maybe, I wouldn't say a pound, maybe a half a pound. Okay, now, since we're mostly made up of empty space, think about this. If I remove these electrons from these atoms and allow these nuclei to come closer together, okay, and I'm just talking about hydrogen, not gold, but just hydrogen. If I were to strip off all the electrons and allow these nuclei to come closer together and bunch up, if anybody, is there any astronomy people in here? Anybody know what a neutron star is? The thing that I'm getting ready to describe is a neutron star, where all the electrons have been ripped off and the only thing that we have are nuclei. If I were to take a spoonful of a neutron star, a spoonful, a teaspoonful, it would weigh more than Mount Everest. The reason being is because that empty space has been closed and these massive objects, these massive nuclei are able to be next to each other.
Can you hold that?
Not me.
Wait. Say. If you.
Go ahead.
What's in it that makes it so
Light?
no heavy?
Heavy. There's just the nuclei. There's no electrons to keep these nuclei spaced out. The reason why we're able to stand and not have our own mass crush us is because we're mostly empty space. That's a really tough concept to think about, because if I were to slice my arm off, I wouldn't find it to be hollow. But if I were to actually go in, if I had the technology to look at atoms, you would see, oh my goodness, there's a few protons and a few neutrons, and then way over are the electrons. There's nothing there.
How does that work?
Isn't that cool?
But we're so like.
Again, we are a large scale. This is such a small scale. I mean, really, really small. That's a tough concept to embrace.
Yeah, I don't get it. Like, cause inside of you is so like they talk about how much stuff is inside you,
Oh, there's a lot.
but then you're telling me that all.
It's mostly empty space.
No.
Exactly.
What does that mean?
Means in between, and here's what I'm talking about. Listen up here, guys. That if this is the nucleus of a hydrogen atom, the electron, which is at cedar, as it's orbiting around in that radius, there's nothing between it. Nothing.
Why?
That's empty space. Why?
Yeah.
Because that's the way it's made. If you think about our solar system, here's the sun. How far are we from the sun? 93 million miles away. And then between us and the sun, there's two other planets. No stars. There's Venus and Mercury, and that's it. Okay? And the rest of that is empty space. So, I mean, if you're looking at that, and that's really not to scale, because that's a lot larger than the nucleus and an electron.
So, like, let's say, like, right outside of, like, hickory and cedar, I guess there's another atom.
There's another electron, and then the nucleus is next to that. So, here we are. Here's cedar and hickory. There's the next nucleus. So this might be, okay, for us, to cedar and hickory, now here is Rockville Road. Okay? So there's, in between that, that's the same radius. Isn't that
But
cool?
there's stuff there. There's obviously.
No, there's nothing there. It's empty.
No, there's like trees and like.
Don't put trees. I'm using it as a scale.
When you say empty space, what does that mean?
It's a void. There's nothing there.
Absolutely nothing.
You've got a nucleus and one electron.
Well, there's obviously objects there.
Well, yeah, from here to cedar there is, but on the atom there isn't.
Okay.
All right.
Alright.
I'm sorry.
You're too literal, is what you are.
Yeah.
I gave another example. If you had a ping pong ball and the first electron, the diameter would be around 2 kilometers. So Rutherford observed the mass of the atom was much less than the mass predicted. So he was like, there's something else in here. We just can't do anything with it. In other words, it's not attracted to a magnet. So he proposed that there was another particle in there because the mass wasn't what it needed to be. And so he said there's a neutral particle in there. I don't know what it is. I can't do anything with it until this guy Chadwick came along, Jimmy Chadwick, and he's credited for doing some work and finding out that, yeah, there are neutrons in there. Okay. So now we've got protons, electrons, and neutrons.
Exactly.
And again, as I stated yesterday, protons are positively charged, neutrons are neutrally charged, or no charge, and electrons are negatively charged. Okay? What's really important is that when we look at mass, the only thing that contributes mass is protons and neutrons. Electrons are really, really small, but that's not what we're factoring. All right, so the threes are part of your homework. Go ahead and get your periodic table out, if you don't already.
Are we only doing?
We're finishing the packet. It'll be quick. The first periodic table that was thought of or designed was based on the physical and chemical properties of what they knew, which wasn't much. All right. Actually, the periodic table did not look like this initially. It looked like actually a square, and I think it may have had like maybe 60 elements. Wasn't very many. Also, it was categorized based on whether they were considered to be metallic or non-metallic. And if you look at your periodic table, can anybody tell me what the majority of the periodic table is? Metals or non-metals? Metals. Very good. And if you look at this, kind of the stair step on the right there, that separates the metals from the non-metals. So metals are all over here. The non-metals are on your right corner.
Calcium's a metal.
Calcium is a metal.
So
Isn't
we
that cool?
drink metal.
We do. We also eat a lot of it too.
There's metal in
Yeah. Now, what we have to stop and think about is we think, oh, metal. This is metal. Well, that's plastic. But like your faucets are metal. It's a way that we describe something, how it behaves with other things. Most of the metals that we associate with, and again in our everyday life, are hard, heavy things that we like to drive around. Okay. All right. Our first periodic table was arranged by increasing mass. That is not how it is now. You'll have some homework on some examples with that. How they react with other elements, that's still the same. Mendeleev came up with a better version of the periodic table. He was a Russian chemist. He's the one that first developed the periodic table. He came up with the periods in groups. Period is a row. A group is a column. Okay. We also can call the groups or the columns families. And it's the horizontal rows were arranged based on increasing mass, and the vertical columns based on how things reacted with other things. Can you breathe? All right, Mendeleev's periodic table had some gaps in it, some holes in it, and he was able to predict the types of properties that those elements would have, even though he didn't know what they were yet. And that was pretty important there. Moseley came around and actually said, Mendeleev, I like what you've done here, but I'm finding too many inconsistencies with your periodic table. And he came up with this periodic table, the way that it's arranged. One of the big things that he changed was how it was arranged by atomic number, or the number of protons, not by the atomic mass. So the periodic table that we're familiar with now is arranged by the increasing proton number, or atomic number. And that eliminated most of the discrepancy. Periodic law. When we talk about periodic law, we're talking about how things in our columns and our rows react based on the trend that we notice. And we'll talk a lot more about this next topic. I just want to introduce this. But if you look at the columns, in other words, starting on with the second period with lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on, how it reacts with, say, hydrogen. Lithium is a 1-to-1 ratio. Beryllium is a 1-to-2. Looking at the boron, it's a 1-to-3, even though it says B2H6, it's a 1-to-3 ratio. And then carbon, it's a 1-to-4. Then it drops back down to 3-2-1. Notice that on the next row or next period, it does the same thing. So these things occur, again, we have a pattern. That's why the periodic table looks the way that it does, when we'll go in more detail later on.
Well, we look more at that when we get
Oh, absolutely. This is just a real quick introduction. Yeah. And that's what this is talking about, the chemical reactivity. Ionization energies. Does anybody know what an ion is?
I've heard of it.
Oh, I know this.
It's in your Gatorade.
Give me nothing here.
That's what I'm asking. Does anybody know what an ion is? I'm not going to give you a definition if I'm asking. An ion is a charged particle. In other words, it has either one more electron than the number of protons, or one less electron than the number of protons. Okay? So it's charged. That's what an ion is. And you need these ions to function in your body. So the ionization energy is the amount of energy needed to remove an electron from that atom. We'll talk more about that later on as well.
Chemical
Families. The periodic table today is grouped in arranged with our families, which are our columns. Okay. And the periods are the rows. Now, let me throw the big periodic table up here. So looking at the periodic table of today, this is how it looks. You'll notice that it's labeled 1, 2, 1A, 2A, and then skip over to 3A and so on. We have these B's here because the B's represent for the transition metals. Our representative elements are the first 2 columns and the last 6. And we need to know this, so pay attention. So the A columns are the representative elements. Why are they called representative? I'll tell you next topic. But know that these are the representative. These are the transition metals in the middle here. Down below, hopefully this will work. Nope, it won't. Down below the last 2 rows are your inner transition metals. In other words, these 2 rows are actually in between these 4 elements. So we slide the whole periodic table over. Now, the reason why we don't have these in here is because the periodic table wouldn't fit on an 8.5 by 11 sheet of paper, and you'd be able to read it. Okay, so that's why most of the periodic tables are arranged like this, or else it'd be that long. Okay. Go back up. Good. There are some family names that you need to know. The first column right here is called the alkali metals. These are some of your blanks. Alkali metals are right here, group 1A. And in the alkali metals, you'll find out that a lot of these form basic solutions when we place these in water. Also, more importantly, we really like these metals because these metals like to make what?
Oxygen.
Batteries. Very good. Lithium batteries. And if you look at your cell phone or look at the battery, it's a lithium ion battery. These metals have great ability, actually up here, the lithium has great ability to remove electrons or to take on electrons, and that's exactly what we need for a battery. Back in the day, it used to be the cadmium nickel, and that was kind of garbage. These things weren't very good batteries, some bad technology. 2A is the alkali earth metals. Alkali earth metals. Skip all the way over here to 7A. These are your halogens. And the last column is your noble gases. So you need to know 4 of these columns. Okay? Alkali, alkali earth, halogen, and noble gases. All right, so here are those 4 columns that I just gave. Talked about the representative elements, so go ahead and grab that blank. So your representative elements, the transition metals, and the intertransition, I pointed those out.
33, 15.
And we're almost done here. And then the last thing, based on how the periodic table looks, in period 1, there's only 2 elements, and we'll talk about why that is when we do electron configurations, next topic. In periods 2 and 3, there's only 8 elements. We'll talk about why that is as well, next topic. And then it goes 32 and, I'm sorry, 16, and then 32. 7 is not completed yet. We're still making those. You won't need to know this for the test, this part right here. Okay. That's just something interesting to look at and go, wow, that's really cool, I guess. All right, so the homework, 3s and 4s. And tomorrow, or the next time we meet, the elements quiz. That is tomorrow for you guys. Tomorrow morning, first thing before breakfast starts.